Hey guys, welcome back. I hope you enjoyed your Thanksgiving break. We've only got 2 more days left worth of assignments for this unit and for this semester, which is pretty exciting. So we've got 3 weeks left and only 2 days worth of assignments. So we are going to be finishing up early. We'll start our next unit over probability whenever we come back in January after Christmas break. So we will take the practice test on Thursday, and then I'll post the test on Friday for you guys to take. So anyway, if we do get to go back in person, which I'm doubtful, but if we do, we'll do a in-class lab experiment, which will be a lot of fun, where we launch gummy bears into space using catapults, really fruit snacks and catapults. But it's a really fun experiment. I hope we get to do it. If not, we'll do it whenever we go back, even if it's in January, February, or whenever we get to go back again. I'll make sure that we have fun and we do that. So let's get started with the second part of experiments and observational studies without any further ado. So the main distinction that you really should notice between the difference between an experiment and observational study is that observational studies are hands-off. We're observing trends in nature. We're not actively manipulating any treatment groups or factor levels or anything like that. We're just observing trends in nature, and we can still kind of post conclusions on what we notice in nature, and we can say there seems to be an association between these two, or some sort of if it's a linear association, we'd say a correlation between the two, but we can't prove a causal relationship between any two variables unless we have a carefully designed experiment. So in an experiment, we have, instead of just observing the ants, we're actively manipulating and kind of hands-on with the ants, and in this case, this poor kid, these poor ants, or whatever, this terrible kid with magnifying glasses burning ants, right? So we're going to be forcing people into treatment groups, whether they like it or not, or forcing lab rats or whatever plants, whatever our experimental units are, into different treatment groups, and then observing the outcomes. And after controlling for certain variables that might cause extra sources of variation or lurking variables, we'll carefully design our experiment, and then we'll be able to say whether or not the difference we observed was statistically significant for a sample of that size, or whether it was inconclusive when we design a better experiment. So we have two different types of observational studies. We have retrospective and prospective. So retrospective, again, this usually comes up whenever we're dealing with rare diseases that we can't just select a group of people and then have them go about their everyday lives, recording their diet and exercise or whatever we're interested in, and then hope one of them gets this rare disease, right? That's not going to happen, right? We're not going to have enough people get this rare disease to be able to say that. So instead, we would look at a retrospective study for rare diseases, where we find the people that have those diseases out of the entire world's population, however many we can get a hold of or whatever, and then we look at factors in their past that might be able to we might be able to just kind of show an association between the two, not showing that it caused it. We'd have to do an experiment at that point, but we look at what was going on in the past, and then we try to then design an experiment from our associations that we showed with our observational study. Okay, then a prospective study, which is if we know that the people are going to be involved, we know what factors we're looking at, we think it's going to be diet and exercise or something like that, we can, with a prospective study, we can actually, instead of having people remember, which is why I got that guy, what's going on? What did I eat on Thursday? Well, instead of having to remember back, we can do a prospective study where we actually say, okay, I want you to list off all of the things that you ate, how much you exercise, what types of exercise, stuff like that. So you can clearly see the benefits. We're going to have, it's going to be much more controlled with prospective than retrospective, but we use retrospective for rare diseases or anything rare. Correlation and causation. So new study found in Colorado has the lowest obesity level of any state. Huh, nice, good to know. You know what that means? No, what? Forget dieting, we're moving to Colorado. So they're reversing the correlation, which is what we might see in an observational study, that we observe people in Colorado have the lowest level of obesity, with a causal relationship. So maybe there's something about living in Colorado, having access to all the wonderful state parks they have, or, not being able to breathe because of the elevation, that kind of forces you to be in shape. You can't be, you can't not be in shape in Colorado, I suppose. I don't know. It's just trends that we saw in here. Now, in order for us to be able to show the causal relationship, which is what this guy is assuming, then we would actually have to have a carefully designed experiment for that. All right, so here's an example, correlation and causation. So in 2000 study, many dogs developed kidney failure. So poor guy, he looks sick, you can tell. All right, so, and then we have this meme guy here. So not go in today. Cough, cough, I am sick. Nice. He's not feeling well. I'm sorry. Sorry, Corey. All right, then we have this lab. He looks really sad as well. Poor guy. All right, so we noticed in all these trends here, we had, I don't know if you saw that, but we actually had in the background, we had this Tres X, or this triple X dog food that these dogs were eating. And it was in the background. I don't know if you noticed that trend in our observational study. It was actually even here. It was just hiding the whole, I know, so clever. It was hiding the whole time. Oh, these jokes are way more fun live in person, but it's okay. I'm going to try to enjoy myself. And from here, you'll notice here that the dog food was also here with the lab. So we noticed a trend with all three of these dogs that they were all eating the same kind of food. So from that trend, we decided to plot it out. So as the sales of this certain Tres X dog food increased, did the vet visits increase as well for those regions or whatever? And if we notice that it did, oh, look, Mom, no hands. Like, so look, correlation, haha. So that just shows that we observed a trend. We didn't actively manipulate anything. We can't prove a causal relationship. There was no random assignment of treatment groups. It was not an experiment, but we did show that we have some concerns, right? From our observational study, we noticed a trend in the data. And so next thing we want to do is actually design a carefully designed experiment. So what was this? I kind of let the cat out of the bag. Or, yeah, observational study or an experiment? Well, we were just simply observing what was happening in nature. We didn't randomly assign anything, so we weren't taking an active role in manipulating dogs into eating certain kinds of food or anything like that. So this would be an observational study. So the scope of the conclusion that we can make would be just that there was an association between the two, not that it was a causal relationship. So there's just merely an association, which we say correlation if it was linear, of course, right? All right, so what kind of study was this? Was it prospective or retrospective? So did we find the dogs first with kidney failure and then we looked back and we saw what was going on? Or did we select the dogs and then we looked at their food logs and what they were eating and stuff like that? So on this one, the common trend you saw in all the photos that the dogs were already sick. So, and probably would be a hint that this is retrospective. So we looked at photos of these sick dogs, poor dogs, and in the background of their sick photos while they were explaining to their mom why they couldn't go to school, we noticed the Tres X dog food. And that was the common trend that we noticed, like in Flint, Michigan. We noticed the water, stuff like that. All right, so an experiment. In an experiment, we have subjects, treatments, and a response variable. So here we have if we design a carefully designed experiment, which we're going to do here, we're going to take all these breeds of dogs. We're going to represent all the different breeds, big dogs, small dogs, all kinds of dogs, right? And then we have the same random group of all these dogs here, of all the different dog breeds. And from these, we pull and we assign some of them to be to have this one type of dog food and one to have the suspect dog food, which is the Tres X. So our subjects in this case are going to be the dogs, which are drawn from our population. So our samples, they should be represented from our population. So a random sample from the population of the dogs. The treatments in this case are going to be the two different types of food. So we have the one that's suspected to be bad, it's causing liver failure, and the other one, which would be a different brand, right? Our response variable is going to be the proportion of dogs that actually develop liver cancer. We're going to see if there is a statistically significant increase in the proportion of liver failure among these random samples of dogs than these random samples of dogs from our population. All right, so the principles of an experiment. First one we have is our control. So we want to control the outside variable to isolate the factors. So we want to make sure, one of those things we would control, many things, is we want to make sure that we feed them the same amount. So we feed them the same amount of the Tres X dog food as we do the other types of dog food. We wouldn't want to mess it up. All right, the second one we have is randomization. So there must be random assignment of the treatment groups. So we can't let the dogs choose which group they're going to be in. We have to assign the treatment group to them. So we can't. The reason for that is you might have lurking variables. So certain dogs might prefer the smell of the Tres X, which also could be because they've already developed liver cancer or something like that. Usually the examples are better, but it's okay. So the main point is that in order to control for any outside lurking variables that might be kind of causing issues and causing to lead us to conclusions that shouldn't be there, we need to make sure we randomly assign the treatment groups. And so the whole purpose of random assignment of treatment groups is to control for outside factors or lurking variables that might cause other sources of variation or bias into our experiment. So make sure that we randomly assign those. Notice that here now we have the same amount of food that we are feeding them. The other thing is that we don't want the dogs to know the difference between the foods. So we're going to make sure that we put them in the same bowls so that they look exactly the same. All right, so I guess that's the other one. So replication. So are the results a one-off? So if we did notice a statistically significant difference among these, we want to reproduce it again. So draw another random sample from our population, make sure that we get it and it's repeatable. That means that there's not too much bias that would actually draw it off, that it was just that one sample that caused some issues on this one. So are the results a one-off? The other thing is, if we only use one type of dog breed, we want to make sure we do the same thing again with another type of dog breed to make sure that it wasn't just a problem with small dogs or big dogs, or with border collies, I think is what they are, and huskies as well, something. So we want to go ahead and make sure that we can replicate the results with different samples, if they were all just random samples, or by blocking with the different breeds and making sure we do it again, and make sure with different breeds. All right, there are some optional principles of the experiment. So blocking is one example. So if we suspect that there might be a source of variation, that might be an issue, like when we talked about the difference between male and female opinions on how we should use school funding for football games or something like that, right? Then we might separate it out, make sure that we block by sex in that example. So blocking would be separation by sex, breed, socioeconomic status. It's funny because I said breed on this one. We would usually say race, but we're talking about dogs. Age, etc. So we do this to reduce the variation, similar to stratifying but in sampling. So just like in sampling, we stratify, so we do like half opinions from the male, half opinions from the female. Otherwise, we could have from one sample to another sample, we could have 60% male and 40% female, which would cause, it to skew towards one direction, right? Or bias is a better word for it, but it's kind of all the same thing, right? So in order to reduce variation from sample to sample, we would make sure that we would block it. So if we thought that it affected male and female dogs differently, then we would do like kind of parallel experiments by blocking by sex, and we do one experiment with the female dogs and one experiment with the male dogs. If we thought it was different by breed, then we would separate it out, and we do parallel experiments by blocking by breed, where we do it with German Shepherds and we do another one with beagles or something like that. Socioeconomic status, don't really have like poor and wealthy dogs, but I suppose kale eating poodles on one side, and on the other side, I'm not even going to throw a dog under the bus because that's mean. Same thing with age. Older dogs and younger dogs we could block, and we could do separate experiments for the older and the younger ones to see if there was a statistically significant difference between older or the younger, like kind of what we're seeing with coronavirus. Would be really important. We see a big distinction between age there, right? Okay, moving on. Optional principles of experiments. So control group, placebos, or a no treatment. So the whole point, we can't just give everyone the Tresaquis dog food because we need to have something to compare it against. So what if the general population, everyone was developing in the liver cancer, and it didn't have anything to do with the Tresaquis dog food? We would need something else to compare it against. So this is where placebos or a no treatment group is going to be put in place. So we'd have to compare it to the same type of dogs or whatever, the same dogs, depending on how we blocked it, if we did, with the same amount of food from something else. All right, also we have blinding, so we can do single blind or double blind. So the most obvious one and essential one is, at the very least, the participants or the experimental units, or the dogs in this case, they must be blinded. So they can't know the assignment of the treatment groups. Now, whoever's designing the study and who's randomly assigning it, flipping a coin, whatever, heads or tails for the different groups, that person has to know, because at the end we have to be able to sort the data back out and then be able to compare between the two groups that we're blocking for, the different treatments or treatment levels or anything like that. But also, another thing that you could do is double blind. So not only do you blind the participants, but you also blind whoever is evaluating, they're measuring the response variable. In this case, the vets who are checking the health to see if they developed any sort of liver issues. So if we don't tell, obviously we can't tell the dogs what's going on, and I'm not sure they would listen, or do they? And then at the same time, we wouldn't tell the vet or whoever was evaluating them, because if we told them, yeah, this dog coming in, they had the Tresaquis dog food, they're probably not going to make it. Feel sorry for them. That might bias the evaluation of the vet, who now heard negative things about this dog. It's like, yeah, it does sound like there's some issues. You get what I'm saying? So kind of planting that seed is not a good idea. So double blind if possible, but at least you have to have a single blind. And another thing we pointed out is it's not possible to be triple blind because somebody has to know who was assigned where so that you can go back and evaluate your data in separate groups. All right, control group with placebo. So I'd like to get this prescription filled at the pharmacy. They'll run about $100. How much is it for the placebo? It's funny because placebos often are like just sugar pills. So the whole point of placebo is that you have this placebo effect. So people who think that they're receiving treatment, so let's say there's depression and you're receiving treatment, some drug for depression, and they're comparing that against a placebo, which is like a sugar pill that does nothing for depression. Although if I eat chocolate, that's not a placebo. That actually helps. Anyway, so whenever we're talking about a placebo and the actual active drug, the whole idea, some people that were given the placebo, which was a sugar pill that did nothing, right? They actually showed improvement as well. So just the thought of receiving treatment, the thought of things improving actually helped and made things actually improve, which is really cool. It's called the placebo effect. I think we talked about it in the last video, but to be honest, it was like 10 days ago when I made that last video, so I don't remember. Anyway, so that's the placebo effect. And so there are some good ways that you can actually do a control group with a placebo. So whoever's administering the placebo needs to be believable. So make sure that they have white lab coats, just like the person giving the injection of the active drug, have the same seriousness about them whenever they're giving out the placebo. If you just like hand it out to like casually, like, you don't give them any instructions about warning, don't consume this with alcohol or something, or whatever the warning would typically be for the other one. If it's just haphazardly, hey, take it, it's harmless, then they kind of get the idea. They know they're in the placebo group, and then they're not expecting change, and then you don't have the placebo effect. So you got to be careful. Also, sometimes you use active placebos. So sometimes instead of just a sugar pill, they will give them something with caffeine. And so they feel like, oh yeah, I'm feeling a rush. Like, they're really energetic or something like that. They give them a 5-hour energy. That'd be hilarious. Or an energy drink. And then all of a sudden they think that, oh, wow, I was in not the placebo group, but the active drug group. And then that might cause their brain to have some improvements as well. And so the whole point is you don't want them to know what group they're in. And so we use placebos for that. And sometimes active placebos, if they give those, of course, those will have some sort of side effect to make the people think that they actually got the real drug that was being tested and not just this placebo. All right, so we have this example from the textbook, which is the OptiGrow experiment. So an ad for OptiGrow plant fertilizer claims that with the product, you will grow juicier and tastier tomatoes. We'd like to test the claim and wonder whether you might be able to get by with half the specified dose. So it's basically they want you to use the full dose, so that you have to buy more fertilizer, but would we get good enough results or as good of results with half the dosage? So that's a good experiment to know, right? You set up an experiment to check out the claim. So of course you have gotten some tomatoes, try growing some plants with the product and then some without and see what happens. But you need a clearer plan than that. How should you go about designing your experiment so you can make sure you control for outside sources of variation or lurking variables, make sure that we can really isolate what's going on with the different treatment levels in order to have enough evidence to say at the end that we should do one way or the other, that whether or not it's worth using the full dose for the cost, right? So designing our experiment, so they took 12 plants and they randomly assigned them into 2 treatment groups. One treatment group was using OptiGrow and the other one was using OptiNo. Clever way of saying it was some sort of placebo or there was no, probably just simply no fertilizer. So what happens if you decide not to use the fertilizer? And then at the end, we compared. What did we compare? I don't know, a level of 1 to 10 for juiciness, and then the overall mass or the average mass or size of it or something like that. I have no idea. So this is basically showing your experimental design here. So we have your subjects, the treatment groups labeled, whatever they are, and then comparing our response variable. We would probably say at the end what that would be, which would be like taste, levels, and mass. All right, so this one is a randomized 2-factor. So if we thought we were not just wondering whether or not the dosage of the fertilizer was one of the factors, we also wanted to see how much water adding, whether or not that would be a factor. So we have 2 different factors. We have the fertilizer and the water at different levels. The water is at 2 levels. We have no water or water added. And then the second factor, which is the fertilizer, has 3 levels, which would be the control with no fertilizer added, then a half dose, and then a full dose of the treatment. So altogether we have 6 treatments, so 6 treatment groups, and just different levels of each factor are being applied there. And so if we had 12 plants, we randomly assigned 2 plants to each one of the groups so that they were all the same size, which is not necessarily always important, but we do want to go ahead and make sure that, because you're going to have different variations with different sample sizes. So if we make them all the same size, we eliminate some of it, makes it easier to compare it at the end. We'll just put it that way. So randomly assign them to their treatment groups. And then at the end, we compare the juiciness and tastiness of each one of those. Now, warning we have here is we only use 2 plants. What if you had like a runt or a plant that wasn't performing as well as the other ones? Maybe it was genetically different or something like that. Then you might have some issues where it shows that full dose and no water was a terrible idea if we used different plants than it would have been. So really small sample size will be really hard to have conclusive results with that one. All right, so what if we block for store quality? So let's say you won more than 12 plants, but you went back to the store and they were out. So then you had to go to another store. Say you went to Home Depot instead of Lowe's the first time, right? And now you bought 6 tomato plants from store B. Well, if we thought that maybe the plants were different from Lowe's, that they were from Home Depot, probably are, probably didn't come from the same nursery, then we would block our experiment. So we block the experiment, like we're running 2 parallel experiments by blocking by the store type, by the store, and then we do the treatment groups there. So we have, this is just a randomized block design with 1 factor level here, just the dosage, not the water as well. So anyway, randomly assign 4 plants into each one of those. No fertilizer, half dose or full dose, and then we compare. We do the same thing with the 6 plants here. So 2 plants are put into each one of them, randomly assigned, of course, so that we can control for any outside sources of variation or lurking variables. All right, so can my boyfriend come along? I'm not your boyfriend. You totally are. I'm casually dating a number of people. But you spend twice as much time with me as anyone else, so I'm a clear outlier. And I'm a clear outlier. What did I just say? Your math is irrefutable. Face it, I'm your statistically significant other. Oh, that's great for a statistician, because statistically significant is what we're all getting about. Is the evidence, is it so much better that it's statistically significant for that sample size, and then significant others, it's the play on words. All right, so let's look for statistical significance here. So if we look at no fertilizer, half dose, full dose, we looked and we graphed out here for their tastiness or whatever. So this is for no fertilizer, so clearly the lowest, and then half dose and then full dose. So it is, there is a difference, and the only question we have is is it a statistically significant difference for that sample size? And so to be able to calculate that, we have to use some stats that we're going to learn in the second semester here. But just from observing, it looks like, yes, we do see an improvement here. It does look, I would say it would be statistically significant without using the actual math to do it. But is the difference between a half dose and a full dose worth the price? Hey, that's a really interesting question, right? All right, the other thing we need to talk about is lurking versus confounding. So lurking variables are outside forces or outside factors that we didn't control for, that we really need to control for, that are going to influence and cause us to think that there is a causal relationship when there really isn't. So for instance, on dry, hot, sunny, summer weather, we have increased ice cream sales and increased sunbirds. So clearly it is the weather that's causing people to want ice cream and to get sunburns. But if we looked at only these 2, then we could mistakenly say that there would be a correlation between ice cream sales and sunburns, meaning that ice cream causes sunburns. You see how silly this is, right? So this is why it's very important when we design an experiment to control for outside factors and to randomly assign the treatment groups, okay? So we would take, for instance, randomly assign people who had sunburns or who didn't have sunburns, whether or not they would eat ice cream or something like that. I don't even know how you set up an experiment for this. This setting up and designing experiments, very, very important. Like all science, one of the best things you can do is to know how to set up a good experiment to be able to show what you are trying to show. Okay, so it takes a lot of practice. Now, confounding is very similar, but also different and kind of confusing. So confounding results from bad designs of experiments where you kind of changed too much at one time, so you weren't able to kind of isolate the variables to be able to say it was specifically this that was different. So for instance, a credit card company, they sent out tons of offers to people, and for credit cards. Now, some of them, they send out a lower rate and no fees. Well, those are both good things that people would want, right? And then other offers they mail to the other half of the people with a higher rate and a $50 annual fee, which are things that you would want to avoid. That's why they're in red. And they found that people preferred lower rates and no fees. They got a higher proportion of those back, people accepting their offers, versus those who were given the higher rate and the 50% annual fee. So the question comes down to what was better, or what was the thing that people, what was the most successful way to bring people in? What was the most important thing for the people that were sending out the information to? Was it that there were no annual fees, or that it was a lower rate, or what was the thing that people avoided the most? Did they not like the $50 annual fee or anything up front, or was it the higher rate that scared them the most? Well, because we didn't break it down into all the possible, in this case we only used 2 treatment groups. We should have used 4 with a combination of lower rate and no fees and higher rate and $50 annual fees to be able to see which one it actually was. So confounding comes about whenever we don't design our experiment carefully with the treatment levels for each factor and each factor level. In this case, we should use 4, we only use 2. All right, so this is the parallel between all the things we've talked about. So when we are doing sampling and we think that there's going to be variation or differences among people because of differences in age, their sex, race, income, or etc., then what we do is we stratify. So we break them down into those groups. We separate them so that we have evenly sampled from each one of those groups, okay? Otherwise, we're going to have sample-to-sample variation of like the amount of male and females, like we've said. Now, in the experiments, if we think there's going to be a difference between any factor, but it could be, again, these are the common ones: age, sex, race, income, sometimes written as socioeconomic status or whatever. Then in experiments, we block. So we run separate parallel experiments for males, separate ones for females, just to see if males responded to exercise and weight loss better than females or something else. I have no idea. All right, then in observations, so again, we can't actively assign treatment groups here. We're just like observing what's going on, but we can actually still do something. We can actually match people that are in the similar demographics, and however you want to break those down, and we call that matching. So we're going to match people that we just observed, like how they did, that were both from similar groups, and that allows us to reduce some variation that we'd have as well. All right, so components of an experiment: controls. So the aspects of the experiment that we know may have an effect on the response, but are not factors that are being studied. So for instance, sunlight, water, soil quality, all things that we want to control. We're not interested in seeing how much sunlight helps plant growth, or the water amount, or soil quality. So instead, we want to control for those, keep them all the same, so that we can actually see how much, and isolate so we can see how much the fertilizer is making the difference, not combinations of fertilizer, water, in case we want to do it that way, which is totally fine. All right, randomize. So we want to randomly draw our samples from our population, then we can repeat them as well. But the most important part about randomization in an experiment is not randomly sampling with your volunteers or anything like that, but rather randomly assigning the treatment groups, and not allowing people to just choose what they naturally would, because that could involve some lurking variables. So in this case, the preference for the dogs for one type of food or the other doesn't matter, because we're going to randomly assign them so that we can make sure that that wasn't some sort of lurking variables going on there. All right, then we want to replicate. So we want to replicate over as many subjects as possible. So results for a single subject are called anecdotes. So it actually takes a sample and a replication of the experiment to be able to show that there's actually something going on here. So your personal experience would be, well, although important to you in statistics, I could care less. We would say that it's anecdotal evidence, right? So unless somebody was claiming that this never happens and then it's happened to you, then you could say, oh, so it has happened, and that would be enough evidence. But in statistics, we need more than just one person. We need samples and trends in order to be able to have anything. All right, so if, as often happens, the subjects of an experiment are not representative sample of the population of interest, replicate the entire study with a different group of subjects, preferably from a different part of the population. So if you didn't randomly sample at the beginning, then you have to replicate it again with different groups. So for instance, if we do a random sample from the population, then we're good. We can do one and we're done, we're fine. Or do another random sample, call it good. But if not, if you only did it with border collies, then you have to replicate it again with other groups to make sure it's not just an issue with the small dogs, but also the big dogs, et cetera, et cetera. Blocking. So blocking is to reduce the effects of identifiable attributes of the subjects that cannot be controlled. So outside sources of variation, we want to make sure that we control the factors that we're not actually interested in, but then we block by anything that we think might be leading to more variation. Like if we think small dogs, for instance, are going to struggle more than big dogs. If we mix the small and the big dogs, groups that had more small dogs would show worse. And so we want to go ahead and block it and do separate experiments or parallel experiments with both types. All right, so 32 minutes. Sorry, it's a little lengthy there. We'll get right into the assignment here on 24. Tomorrow's will be much shorter because I won't have to go through all the information again. So we'll just go right to the assignment. All right, recall the experiment investigating the effectiveness of the exercise with no dessert and the combination combating insomnia. So recall the 40 insomniac volunteers randomly assigned to 4 treatment levels. So why didn't the experimenters just have everyone exercise to see if their ability to sleep improved? So the whole point is we want to have some control group in order to compare it against. So if there was just overall general improvement, maybe it's because the weather changed and everyone experienced more pleasant weather, which allowed them to sleep better. Then we would have said that, oh, it must have been the exercise that we had everyone do. Instead, it was really something else that was going on in the world or something that caused everyone to sleep better at night. So we do have to have a control group so that if there was some other outside factor, we would see that among the control group to say that it wasn't just the weather that was improving their sleep quality, it was actually their exercise. So again, you have to have a placebo or a control group in order to compare against. Why is it important to randomize in deciding? So the whole point of randomization and sampling is to reduce bias. The whole point of randomization in an experiment is to be able to control for outside lurking variables that might cause some issues. So for instance, if we just let people choose whether or not they wanted to exercise, then maybe our more athletic people who always exercise, maybe they tend to have better sleep because they're tired because they exercise. I don't know. And so that would mess up our results, where we wanted to say that it was the exercise, not just what happens among people who are in the habit of exercising. So we're going to make people uncomfortable with experiments. All right, what would be an advantage or disadvantage of using a larger sample size of 100 subjects instead of 40? So a pro is anytime we have a larger sample size, we're going to have less variation. Now, we can still have bias that moves it off target, but we're going to have less variation in the sample sizes. This is going to be where margin of error comes in, sampling distribution models, which we'll talk about in second semester. But all you need to know for now is larger samples have less variation. So for instance, let's say we're looking at the average height of Americans, and let's say one person is like 7'7". Well, if that person was selected, they're going to heavily skew the average for that group. But if we had a larger group, this one outlier out of 100 is not going to skew it as much as one outlier out of 40. So just mentally, that can help you understand what's going on here. A con, anytime we use larger sample sizes or more subjects, in this case, more volunteers, that's going to take more time and more money. So it's always going to be a con for those. 26, suppose that some of the 40 subjects had maintained a healthy weight, but others were quite overweight. Why might researchers choose to block the subjects by their weight level before randomly assigning some people to the exercise program? So for instance, if somebody had, if we thought, in this case, we thought that people who were overweight were going to have different results, maybe be more severe or less or whatever we thought was the case, we want to go ahead and block by their weight level in order to reduce outside sources of variation. So for instance, if we had more overweight people that were in one treatment group than in another treatment group, then that might kind of skew our results to make us think that, okay, so it's really this that's causing the difference instead of that one. So we're going to go ahead and run 2 parallel experiments with the people who are overweight, and by blocking by the weight, and then another one with people who are not overweight. So statistically significant is when an observed difference is too large to have occurred by chance. Now we'll be able to quantify this value with p-values next semester, but for now you just need to know it's an observed distance or difference that's too large for us to believe that it likely occurred by chance. So it's not natural. There's something going on here, essentially what's going on. That's when we would say the difference was statistically significant. So subsequent chapters will show more specific calculations and give rules, but the principle remains the same. It was unlikely to have occurred by chance. It's the phrase you need to use on the AP test and stuff. All right, so control groups, participants assigned to be a baseline treatment level, typically the default no treatment, which is well understood, or a null placebo treatment. The response provided a basis for comparison in order to determine if the effects of treatment levels are statistically significant. So we do have to have a control group, whether it's done by placebo or just we're not going to have a change or they don't get a treatment. All right, blinding, an individual associated with an experiment who's not aware of how the subjects have been allocated to the treatment groups is said to be blinded. You can do single blind when the only participants don't know or the person who gave it to them didn't know. Well, I'll read it to you. So when every individual in either of these classes is blinded, an experiment is said to be single blinded. All the participants do not know the random assignment, or all the researchers do not know. So two different ways to do it. Double blind is when everyone in both classes is blinded. We call this experiment double blinded. Participant and researcher do not know, but somebody has to know in order to be able to search data. So it can't be triple blind. All right, 39, reading. Some schools teach using phonics, or the sounds made by letters, others using whole language word recognition. Suppose a school district wants to know which method works better. So suggest a design for an appropriate experiment. Create a diagram for the experiment. So we're going to take all of our students, we're going to break them into two groups. So one's going to be taught using phonics and one's going to be taught to learn to read by using whole language, which is sight words, in other words. All right, so they're going to be randomly assigned here. These are our different factors, which is going to be phonics, or our factor with two different levels, two different ways of learning reading. And then at the end, we're going to measure reading performance. However, we do that testing more than likely. So our factors in this case are going to be, well, I suppose you could say the factor levels. It's a little, So the factor is going to be phonics and whole language. Our response variable that we're measuring is their reading performance, and what role does randomization play. So randomization is going to reduce the variation that we would have, or the effects of any lurking variables there. So we're not just allowing students to choose which program they were in, we have to randomly assign them. So if we had, if our higher performing students were naturally going to prefer phonics over whole language, then that might change our results. So we need to make sure we're randomly assigning them. We also would want to make sure we control, so we're using students from the same grade level, or using the same teacher, having the same teacher teach both phonics and whole language, stuff like that, because otherwise there'd be other sources of variation from performance there. All right, so sorry this one was a bit longer one. Again, we've only got 2 more lessons to do. After today, you've only got 1 more, then a practice test, and then we'll take our last test before Christmas. So make sure you're turning in all of your work. Any late work that you have or incomplete assignments, you can still turn in for full credit. Make sure you get those in and to me then. So I'll see you guys later. Have a good day.